All right, in this video, we will be going over section 1.2. In this section, we are going to give formal definitions of various types of limits, okay? Here in this section, we will be using these notations. Let's get familiar with this notation, okay? To write for all, I use this symbol, for all symbol. And then to say there exist, I use this symbol, okay? Whenever you see this symbol, that is for all. Whenever you see this symbol, that is there exist, okay? All right, before I give a formal definition, I want to introduce something called a punctured interval, okay? Let's understand what we mean by a punctured interval, okay? Suppose this is your real line and you have a point C on the real line, and then I take a positive length delta. Delta is a positive number. Think of that as a length. And then I take the point C plus delta. That should be to the right of C, right? Because it's a bigger number. And I take the point C minus delta. I subtract delta from C, then I should get a point to the left of C. Okay. Now what I do is I take this interval, this open interval from C minus delta to C plus delta, and I remove this point. I remove the point C. I remove my point C. The point C has been removed from that interval. Okay. What I did was I took this entire interval C minus delta to C plus delta, and I remove this middle point C. Okay. That's what we call a punctured neighborhood. This C minus delta to C and then C to C plus delta. This set is called the punctured interval, and that can be written as C minus delta comma C, that is from here to here, but you have to skip the point C because C is not included. And then you have to take everything from C to C plus 1. Here is how you write the interval notation. C minus delta comma C union C comma C plus delta. Okay, all that means is that you take everything in this open interval except this point. Okay, this is the set notation for that particular set. Okay, this is what we call a delta punctured interval, sometimes called punctured interval. Sometimes you say delta punctured interval. Delta means this length is delta. As you can see, this length is delta. This length is also delta. All right, that's what we mean by a punctured interval. Okay. Having introduced this punctured interval, let's go to our definition. First definition, definition 1.5, formal definition of limit. Here is where we give the formal definition of limit. Okay. Last time we were talking about the geometric aspect of limit, but here we give the formal definition. The limit as x goes to C, f of x is equal to L means that for all epsilon greater than 0, there exists delta greater than 0, such that if your x is in this punctured delta neighborhood, then your f of x has to fall in this interval, L minus epsilon, L plus epsilon. Okay. By the way, we say that this limit exists if this L is a real number. Okay. If that limit exists as a real number, then we say that the limit exists. All right, let's try to understand this definition a little bit more. Again, we are going to use geometry to understand what this means. Okay, I'll copy the definition to the other side. Again, the statement is limit as x approaches to C, f of x is equal to L means that for all epsilon greater than 0, there exists delta greater than 0, such that if you pick your x in this delta punctured interval, then your f of x has to fall in this interval, L minus epsilon, L plus epsilon. Okay. Let's think about a graph like this. This is the graph of y is equal to f of x. And let's say your point C is here and your L is here. And then L plus epsilon has to be somewhere here, right? Because we take our epsilon to be positive. For any epsilon greater than 0, we need to be able to find delta such that if x is in this punctured neighborhood, f of x is in this interval, okay? So L plus epsilon is somewhere up here, and the L minus epsilon is somewhere here. What does this definition tell you? There should exist some delta such that if you pick your x in that delta punctured neighborhood, then your f of x, your y value, should land in this interval. So that means you should be able to find the delta punctured neighborhood around the point C. Delta punctured neighborhood means this open neighborhood without this point C. You remove the point C. Okay. As long as you pick the x values from that delta punctured neighborhood, your y value should be in the interval L minus epsilon to L plus epsilon. Your y value should land in this interval. Okay. For example, this is clearly possible in this case. Why is it possible? Think about the delta punctured interval like this. Now, if you pick any x value in this delta punctured interval, by the way, when you say delta punctured interval, this point is not included, okay? C is removed. Everything else is included. Now, if you take any x value in this delta punctured interval, your y value is going to fall within the interval L minus epsilon, L plus epsilon, right? The interval L minus epsilon, L plus epsilon means this interval. So whenever you pick a value in this delta punctured neighborhood, your y value is going to be in that interval. So even if you take this value right here, your y value is here. So your y value is going to fall in the interval L minus epsilon, L plus epsilon. Also on the other side, if you take this value, your y value is here. Okay, so that means this would be a good candidate for delta. Whatever the length that you took here, the length from C to the left endpoint of the interval, this length is your delta. Of course, this is also delta in that case. That delta is going to work in this case. So that's the geometric idea. For any epsilon, doesn't matter how small this epsilon is, you should be able to go ahead and find such a delta such that whenever you pick your x point, x value in that neighborhood, your y value should land between L minus epsilon and L plus epsilon. If that is possible for any given epsilon, we say that the limit as x approaches to C, f of x is equal to L. Okay, that's the geometric idea here. All right, let's move on. Here is an example. Let's do this example before we go to the next definition. Use a graph to illustrate and approximate the largest delta, which guarantees that if x is in this delta punctured interval, then your y value, your f of x, is in this interval 3, 5. Okay, looks like this statement very well coincides with this statement, right? If x is in this one, this delta punctured interval, your f of x has to fall in this interval. Okay, but here clearly we can identify our C. Our C in this example, the value of C is 2, right? This plays the role of C. So clearly the value of C can be understood to be 2. This is C, this is C. Okay, but epsilon is not visible in this example. What is my epsilon really? If you compare this one against what we have here in the definition, I have copied it here. See, my f of x has to fall in this interval, L minus epsilon, L plus epsilon. But here I don't see any epsilon. But notice that we can view this interval as this, the midpoint of this interval is 4, right? So we can write this interval as 4 minus 1, 4 plus 1. Because 4 minus 1 is 3, and this is 4 plus 1 is 5. So as you can see, your epsilon looks like 1, right? L minus, in that case, your L is going to be 4. Your L is going to be 4. Okay. Now I'm going to draw the graph of my function f of x. I know how to draw the graph of my function f of x. That's a parabola. F of x is equal to x squared. So it looks like this. And here is the point x is equal to 2. When x is equal to 2, I know that I can plug in the value 2 here. I can find the function value. My function value is 4. I found. Okay. Notice that here again, my epsilon is 1 because this interval can be viewed as 4 minus epsilon, 4 plus epsilon, and we identify our L to be 4, comparing with this definition. Okay. All right. So now let me mark that here. This is actually 4 plus epsilon, 4 plus 1. Pardon me. This is 4 minus 1. So clearly your epsilon is 1. Okay. So what does the question ask now? Use a graph to illustrate and approximate the largest delta, which guarantees that if you pick your x in this punctured neighborhood, delta punctured neighborhood, your f of x should fall between 3 and 5. That means your f of x should fall in this interval. This is the interval 3, 5, right? This number is 3. This number is 3. This number is 5. Your y value should fall in this interval. Okay. That way, what is the largest delta that you can pick? Clearly, you can pick some delta. Clearly, you can pick some delta so that your y value is landing in this interval. For example, think about this delta punctured interval. If you take a delta punctured interval like this, very small interval, very close to 2, then notice that if I track this down to the y-axis, this is the y value corresponding to that. If I track this down to the y-axis, this is the corresponding value. As long as you pick an x value in this delta punctured neighborhood, your y value is always going to land somewhere here, right? Somewhere in this interval. That means your y value is going to land between 4 minus 1 and 4 plus 1. That means between 3 and 5. So such a delta can be found, but the question is, what is the largest delta that you can find, so that as long as you pick your x value from this delta punctured neighborhood, your y value is landing between 3 and 5. What do you think? This is a good time to pause the video and think about that for a minute. Okay. Well, think about this way. Can I make it a little bit larger and still survive? This delta is bigger than the previous delta, right? That delta is bigger than the delta that we took for this one. So can I survive with this delta punctured neighborhood? Well, that way you can keep arguing. You can keep making the delta interval bigger and bigger. So to get the largest value, what I'm going to do is I'm going to do a small construction. I'm going to find the x value corresponding to this value, this y value. I want to find the x value corresponding to this y value, which is 3. Right here, that x value is right here. And also I want to find the x value corresponding to this value. I want to find the x value corresponding to this y value. Okay. How do I find this x value and this x value? Very simple, right? You set x squared is equal to 3 to find this x value. This is nothing but square root of 3. You take the square root of both sides. So you will get x is equal to 1.732. And then similarly, by setting, let me write it here. This point is 1.732. Now what I'm going to do is I'm going to set x squared is equal to 5. This is my y value now. I want to find the corresponding x value here. Okay. So I set x squared is equal to 5. That will give me x is equal to square root of 5. So x is 2.236. So I found this x value. This x value is 2.236. Now we are ready to answer the question about the largest delta value that we can pick. See, if I pick, as I told you earlier, if I pick my delta punctured neighborhood to be this neighborhood, delta punctured interval to be this interval, clearly for any x value you pick in this interval, your y value has to land between 3 and 5. Okay. Likewise, how big can I make this delta punctured neighborhood? Can I make this big? Can I make this big? Can I make this big? Clearly not, right? If I make my delta punctured neighborhood this big, if I take a point somewhere here, my y value is going to land outside of that interval 3, 5. This is not between 3, 5. So likewise, think about how big can we make my delta? Well, for that, to figure that out, I'm going to compute this length. I will compute this length, and I'm going to compute this length. Okay. As you can see, you can compute this length by subtracting this first length. By subtracting 1.732 from 2, you will get 0.268. 0.268, and the other length will be 0.236. Okay, this length is 0.268. This length is 0.236. Okay, now you should be able to tell me what is the largest delta that you can pick. The largest delta that you can pick is the smallest of these two numbers. Okay, the smallest of these two numbers is 0.236. That means you can take your delta punctured neighborhood to be this neighborhood. Okay, your delta is this length. If I take my delta to be this length, when I measure the delta to the other side, I'm not jumping out of this point. I'm not going passing this point because the minimum of these two lengths is this one. Okay, that will ensure that I am inside this big interval. Okay, so my delta, largest possible delta in this case is just possible delta is equal to 0.236. That's the largest possible delta. You cannot make delta bigger than that, because if you make your delta bigger than that, you will jump out of this point. So that means you're going to collect points outside of this this interval. Okay, if you take a point somewhere here, you're going to land outside of the interval 3, 5. Your y value will be outside of the interval 3, 5. All right, so we found the largest delta. Let's move on. Okay, next we have the formal definition for the left limit. Here is the formal definition. The left limit as x approaches to c from the left-hand side, f of x is equal to L means that for all epsilon greater than 0, there exists delta greater than 0, such that if x is in this interval c minus delta comma c, then f of x has to fall in this interval L minus epsilon comma L plus epsilon. What is the difference between this definition and the previous definition? This is the definition for the two-sided limit. Okay, here in this definition, we are talking about the limit as x approaches to c from the left-hand side. Left-hand side means if you go to the two-sided limit definition, we are talking about x values in the left part of the punctured interval. Okay, this is the whole punctured interval, but I'm not interested in points to the right of c. I am interested in x values to the left of c, because I'm talking about the left limit. Okay, so what I'm going to do is I'm going to chop this part off. If I chop this part off, that's when you obtain this definition. See, I just have c minus delta comma c. I don't have that union, the other part. Okay, so it's kind of a modification of the original definition to get the definition for the left limit. Okay, in the left limit case, only you take the left part of the punctured neighborhood. You don't take the right part because you are not interested in knowing what's happening for the x values, what happens to your function value when x approaches to c from the right hand side. You are only interested in knowing what happens to your function value as x approaches to c from the left hand side. So you take the left part of the punctured interval. Similarly, when you define the right limit, limit as x approaches to c from the right hand side, f of x is equal to L means for all epsilon greater than 0, there exists delta greater than 0 such that if x is in this interval, then your f of x should fall in this interval. Okay, as you can see again, here also we take only the right part of the punctured interval because we are interested in the right limit in this case. Okay, we are interested in knowing what happens to my f of x as x approaches to c from the right hand side. So that's why I'm taking an interval to the right of c, from c to c plus delta. Okay. All right. Next, we have this theorem. For a limit to exist, left limit and right limits must exist and be equal. Okay. So this is the theorem as a statement. Formal statement. Limit as x goes to c, f of x is equal to L. That means this is the two-sided limit. If and only if the left limit exists and it is equal to L, and the right limit exists and it is equal to L as x goes to c. Okay. So what do you mean by this if and only? If and only if means if this is true, this has to be true. And if this is true, then this has to be true. Okay, it should imply both directions. If this is true, this has to be true. And if this is true, this has to be true. Okay, that's what we mean by if and only if. Actually, the proof of this theorem is so straightforward. It is just an unwinding of the definition. I'll show you a one side. Okay, let's assume that this is true. And the other direction is left as an exercise. Okay, assume that limit x approaches to c, f of x is equal to L. What does that mean? We have the definition. Here is the definition. That means for all epsilon greater than 0, there exists delta greater than 0 such that if x is in this punctured neighborhood, your f of x should fall within L minus epsilon, L plus epsilon. Let's unwind it there. Okay, that means for all epsilon greater than 0, this symbol is for all. Okay, this says for all. For all epsilon greater than 0, there exists delta greater than 0 such that if x is in c minus delta comma c union c comma c plus delta, then my f of x should be in L minus epsilon, L plus epsilon. That's the definition, right? That's my definition. Okay. So this means for all epsilon greater than 0, there exists. This is the symbol for there exists. Okay. Delta greater than 0 such that if my x is in this delta punctured neighborhood, then my f of x should fall in this interval L minus epsilon, L plus epsilon. Okay. Now, if this is true, when x is in this, if your f of x fall in this interval, if your x is in this big set, how if I chop off one piece? Should that still be true? That should be true, right? Because for all x in this delta punctured interval, your f of x should fall in this interval. Even if I chop this off, still that should be true, right? If it is true for the bigger set, it should be true for the smaller set. So if x is in c minus delta comma c, then your f of x has to fall in this interval. Okay, so that means even if I chop this piece, still your statement should be valid. But what is this? What is this? This is exactly the definition of the left limit. As you can see, that is exactly the definition of left limit. That means limit as x goes to c minus f of x has to be L. This means limit as x goes to c from the negative side, f of x has to be L. Okay. Similarly, you can show that limit as x goes to c from the right hand side, f of x is also L by chopping off this part instead of the second piece. Okay. In the left definition, we chopped off the second piece, but in the right definition, right limit definition, you chop off the first piece. All right. Let's move on to the next definition. Limits involving infinity. Okay. The infinite limit, here is the definition of infinite limit. Limit x goes to c as x approaches to c, f of x is equal to infinity means that for all m greater than 0, there exists delta greater than 0 such that if you choose your x in this delta punctured neighborhood, delta punctured interval, then your f of x should fall in this interval m comma infinity. What this tells you is that your f of x has to be bigger than m. F of x falls in this interval means your f of x is bigger than m. This is an equivalent way of saying that. Okay, f of x is in this interval means f of x is bigger than m. All right. Okay, let's try to see what this means geometrically. Suppose you have a function like this. This is the value c, where you have the vertical asymptote, and here is your function, graph of the function f of x. Okay, all right. So what does this mean? What do we mean by, first of all, notice that geometrically it is clear that as x approaches to c, f of x is infinity. Because as you can see, as x approaches to c, from either side, your y value is growing without bound. So the limit is infinity. This is clear from the graph. Okay. What does that mean in terms of this algebraic definition? Well, for any given m greater than 0, doesn't matter how large this m is, you should be able to find the delta greater than 0 such that if x is in that delta punctured neighborhood, this delta punctured neighborhood, then f of x is in this interval. Or in other words, f of x is bigger than m. Can we do that? For example, think about this. Let's take your m value to be somewhere here, 1 billion or something, somewhere here, okay? Some very large number. M is here. Then I can draw a horizontal line like this. Then can I find a delta punctured neighborhood around C so that if my x is in that delta punctured neighborhood, my f of x is in this interval, or in other words, my f of x is bigger than m. Can I find such a delta? Well, clearly, if you find a very small delta, if you use a very small delta like this, you can easily find a delta punctured, very small delta punctured neighborhood. And if you pick a value, x value from this delta punctured neighborhood, your y value is going to be above m. Let me draw a small delta punctured neighborhood. For example, this is my delta punctured neighborhood, okay? This point C is not included in that interval. Now, if you take any x point in that delta punctured neighborhood, your y value is going to be this one. This is bigger than m. Your f of x is bigger than m. That's what you want, right? No matter what point x value you pick from this delta punctured neighborhood, delta punctured interval, your y value is going to be bigger than m. That's what exactly you want. So for any given m, if you can find a small delta punctured neighborhood, so that if your x is in that delta punctured neighborhood, your y value is bigger than m, then this limit statement is true. Okay, that's what we mean by this limit statement. Okay, that's the geometric idea of this limit statement in terms of this m, delta, and c. Okay, all right, let's move on. And by the way, this definition can be modified for the one-sided limit case. For example, here you say as x approaches to c, right? When you say as x approaches to c, that means as x approaches to c from either side. Okay. What about if you want to talk about the one-sided limit? For example, as x approaches to c from the left-hand side, or as x approaches to c from the right-hand side. Okay, we can modify this definition. All what you do is, if you want to talk about the limit as x approaches to c from the left-hand side, you only take the left piece of this delta punctured interval. Okay, you chop this off. And if you are talking about the right limit, put in a plus sign here, you chop this part off, you only take the right part of the delta punctured neighborhood. Okay, a similar argument as I explained in the previous case. All right. And here are those modified definitions. Okay, limit as x approaches to c from the left-hand side, f of x is equal to infinity means that for all m greater than 0, there exists delta greater than 0 such that if x is in this interval, you see, I only take the left part of the punctured interval. Okay, then my f of x should be in this interval. That means f of x is bigger than m. Okay, similar definition can be given for the right limit. Okay, I will let you read that part. In that case, you only take the right part of the delta punctured neighborhood or delta punctured interval. Or sometimes some authors says delta punctured neighborhood. Okay, either terms are fine. All right, now let's look at an example. Okay, here is the example. Use graph and algebra to find largest delta that corresponds to m is equal to 100. Here is the given limit statement. Okay, for this given limit statement, you need to find the largest delta corresponds to m is equal to 100. How do we do that? First of all, let's try to find the correct definition for this limit statement. Okay, this is clearly your f of x, right? This is your f of x. What definition would go with this one? Well, if you go back and look, this definition will go with that one because there's an m involved, there's a c plus, here you have 1 plus here, that's the right limit, and infinity, your limit is infinity. Okay, looks like this is the definition that goes with that example. Okay, so m is given. In my case, my m is given to be 100. That is known. All I need to do is I need to find the largest delta, largest possible delta. Okay, how do you find the largest possible delta? How do you find the largest possible delta such that if you choose your x in this interval, c comma c plus delta, then f of x has to be bigger than m? Well, again, geometry is going to help us. What we do is you graph this function f of x. If you graph the function f of x in the right hand side, remember in this case, you don't have to graph this on the entire real line. You can just draw the shape of this graph of f of x only to the right of 1, because we are only talking about the right. Okay, so if I graph this one, I'm going to get a graph like this. Okay, so this is how the graph looks like. As x approaches to 1 from the right hand side, your y value is growing without bound. Okay, so now my m is given to be 100. So let me mark my m. Let's say m is somewhere here. This is my 100. This is the value of m. Okay, now I need to find the largest delta. If you go back to the definition, I need to find the largest delta such that if I choose my x in this interval, c comma c plus delta, then f of x has to be bigger than m. Okay. For that, what I'm going to do is I'm going to compute this value. I'm going to compute this x value. The x value corresponding to this y value, 100. Okay, I'm going to compute this particular x value. How do you compute that x value? Well, I'm going to set 100 is equal to my function 1 over x squared minus 1. So multiplying both sides by x squared minus 1, we get 100 times x squared minus 1 is equal to 1. Simplifying this further, you get 100 x squared is equal to 101. Okay, and then x squared is equal to 101 over 100. Now you can find x by taking the square root of both sides. 100, the square root of that. This value would be 1.0049. That means this value is right here is 1.0049. Okay. Now, can you guess what is the largest delta that you can pick? What is the definition again? We need to find the largest delta. Largest delta greater than 0 such that if x is in 1, 1 plus delta, then my f of x has to be bigger than 100. 100 is my m, okay? So if x is in this interval, then my f of x has to be bigger than 100. What is the largest such delta? For example, 1 comma delta to be, if I take my delta to be very small, something like this, then if I take this interval, 1 comma delta, 1 comma 1 plus delta, clearly, if I take any x value in this interval, my y value is going to be bigger than 100, right? What about if I take a little bit bigger interval, 1 comma 1 plus delta like this? Still, if you take any x value in this interval, your y value is going to be bigger than 100. Likewise, what is the biggest delta that you can take? 1 comma 1 plus delta. So what is the biggest delta that you can take? The biggest delta that you can take is this length, right? If you take this length, and if you take this 1 comma 1 plus this number, so if you take this one to be your delta, then that is the largest delta that you can take. Okay, so you take this length. Let's find this length, by the way. This one is 0.0049. So the largest possible delta is 0.0049. Okay, if you cannot make your delta bigger than this one, in that case, if you take your delta to be bigger than that, what happens is that when you take 1 comma 1 plus delta, it will pass this point. It will come up to here. Your delta interval 1 comma 1 plus delta would be an interval like this. In that interval, now if you pick a point somewhere here, your y value is less than 100. You see, your y value is less than 100. No, you want your y value to be bigger than 100. If you want your y value to be bigger than 100, the largest possible delta is, this is the value of delta, this length. Okay. All right. Let's move on to the next slide. Now, the definition 1.9, which is about the limits involved in infinity. Okay. The limit at infinity, that means limit as x goes to infinity f of x is equal to L, means that for all epsilon greater than 0, there exists n greater than 0 such that if x is in the interval n comma infinity, then f of x is in the interval L minus epsilon comma L plus epsilon. Okay. Geometrically, what it means is that, think about a graph like this. Here is the graph of f of x, and here is the value L. Y is equal to f of x. Maybe I will put it here. Y is equal to f of x. Now, as you can see, clearly this limit statement is true for this one, because when x goes to infinity, your y value is getting closer and closer to L, right? As x goes to infinity, your y values are getting closer and closer to L. That means limit as x goes to infinity, f of x is equal to L. What does this mean? That means for all epsilon greater than 0, there exists n greater than 0 such that if you choose your x in this interval, n comma infinity, then your f of x should land between L minus L, epsilon and L plus epsilon. Okay, let's draw L plus epsilon and L minus epsilon here. I will extend this a little bit. Say this is your L plus epsilon. This is your L minus epsilon. Okay, so if I draw this interval L minus epsilon, L plus epsilon, this is that interval. Okay, so this means for any epsilon you choose, you should be able to find some n, large enough n, such that if you choose your x in this interval, x is in this interval means x is bigger than n. If x is bigger than n, your f of x should be in this interval, L minus epsilon, L plus epsilon. For example, suppose you choose your n to be somewhere here. Okay, suppose you choose your n to be somewhere here. Then would that serve as an n for this definition? Okay, clearly yes, right? Because if you choose your x value in this interval n comma infinity, now I'm taking my n to be here. Okay, if I take any x value here between 0 n comma infinity, then for example, suppose you pick your x value to be somewhere here, then your y value is here. Oops, that is a little bit lower than L. So as you can see, that y value falls in this interval. Okay, all right. So that means such an n is possible for this particular graph. Okay, and then the infinite limit at infinity. What do you mean by limit as x goes to infinity, f of x is equal to infinity? That means for all m greater than 0, there exists n greater than 0 such that if x is in this interval n comma infinity, then f of x is in this interval m comma infinity. Okay. All right, let's do some examples now. This is example 2, I guess. Use the graph to illustrate and approximate the smallest n, which guarantees if x is in the interval n comma infinity, then x plus 1 over x is in this interval. Okay. First of all, let's try to understand what definition would go with this one. Okay. What do you think? Which definition would go with that one? Okay, clearly this definition will go with that one, right? Because you clearly have a limit, like you want your f of x to fall in this interval. You want your f of x to be between L minus and L plus epsilon, and you want to find an n, okay, such that if x is in this interval, your f of x is in this interval. Here, the epsilon is not clear, but what we can do is we can find the epsilon associated to this example. The midpoint of this interval is 1. So this can be viewed as 1 minus 0.25. This is 1 plus 0.25. So clearly your epsilon is 0.25 in this case. Let me write it. 0.25. Okay. So what are we asked to find? Use the graph to illustrate and approximate the smallest n, which guarantees that if you choose your x in this interval, if you choose your x to be bigger than n, then your function f of x should fall in this interval. Okay. First of all, I'm going to mark 1 here because the midpoint of this interval is 1. I'll mark 1 here. And then this is 1 plus. This is 1 plus 0.25. And this is 1 minus 0.25. Or you could say, you could just write 0.75 itself here. Okay. Here 1.25. 0.75, 1.25, pardon me. 1.25, this is 0.75. Okay. Now, how do I find the smallest n? You asked to find the smallest n such that if x is bigger than n, then my f of x is in this interval. Well, what I'm going to do is I'm going to find the x value corresponding to the y value 1.25. I'm going to find this x value. To find that x value, I'm going to set my function x plus 1 over x to 1.25. And if I solve this equation, let's see what we get. All right, if we solve this equation, can multiply this x to the other side and move this x to the right hand side. And if you solve that one, you will get x is equal to 4. That means this value is 4. Now, if I take my n value somewhere here, clearly for all x in this interval, for all x bigger than n, your y value will fall in this interval. Your y value will fall in this interval. Y value will be between 0.75 and 1.25. Okay, is it clear? If you take your n here, for any x value in this interval, for example, say your x value is here, then your y value is here. That falls in that interval 0.75, 0.75, 1.25. Okay. Likewise, if you take your n to be to the right of 4, this point, to the right of this point, then you are going to, this definition is going to satisfy. But what is the smallest n that you can pick? Can you pick your n to be this value? Again, yes. For any x value in this region, your y value is going to be between 0.75, 1.25. Likewise, as you can see from the geometry of this figure, this is the smallest n value that you can pick. Okay. Is 4. All right, with that, we can conclude the section 1.2. Here are the assigned homework problems. Make sure that you work on these problems. All right, I'll stop there and I'll see you next time.